Welcome to the Coherence Times, where we dive into the science and the story of quantum computing. I'm your host, Ryan Mandelbaum. Every other week, I sit down with researchers, technologists, and thought leaders to unravel the incredible challenges and breakthroughs shaping this generational technology. So, whether you're a tech enthusiast, an industry leader, or just somebody who's curious about how quantum computing might change the world, well, then you're in the right place. Together, we'll demystify the concepts, bust the myths, and explore not just how quantum works, but how it can work for you. Today, I am really excited to be here in person with Matthias Steffen, an IBM fellow and the leader for quantum processor technology at IBM. Matthias is a veteran in the field of superconducting quantum computing processors, and he has watched this technology mature from a futuristic lab experiment to a cloud-based processor on the verge of delivering real computational advantages. So today, he leads research and development of the technology, and he has had an enormous hand in the development of IBM's quantum computing chips. Matthias?
Ryan, good morning.
Good morning. How is it going?
Good. Excited to be here.
It's good to be here. You're just at work, so I know it's pretty good to be here. So let's just get some background. So I want to talk to you about the history of quantum computing. So maybe we'll talk about your history of quantum computing. So how did you get started just in the field and get started at IBM?
So I remember reading an article in college, so mid to late 90s, about quantum computing. I don't know where exactly this article was featured, but it sounded very interesting. And I was also very drawn to quantum mechanics at that time. I was a physics major, but didn't think too much of it afterwards. I graduated, went to grad school at Stanford, and I had to start finding a lab. So this was back in 1998. And it just so happened I ran across a professor who said, "Oh, we also have quantum computing over in IBM Almaden with Ike Chuang. Is this something that would interest you?" I was like, well, yeah, absolutely. I'd love to think about that.
So Ike Chuang is like the Ike Chuang, like the guy who wrote the textbook.
Correctly. The Ike from Mike and Ike.
Yeah, Mike and Ike is like the most famous quantum textbook that anybody's,
Yeah, that was actually being written, or even maybe slightly before it was started to be written. So it was quite a while ago. So I wanted to join this field because I've been interested in building devices, and not just in terms of writing papers, but actually build a technology, build something somebody eventually can use. I wasn't so much interested in standard semiconductor fab. I don't quite remember what node size technology we were at that time, but it was clear that at some point you're going to hit a dead end with standard semiconductor fab. So I figured, well, this might be something that looks like it could not replace, but augment computing. So I decided to get into that area.
So you were like, the chips, they're getting cooler and cooler, but they're not going to be getting that much cooler for long. And so you said, how do we build a really cool chip?
Something very different.
Cold chip.
Well, it wasn't cool. At that time, the work was with liquid state NMR, so nuclear magnetic resonance. So it wasn't chips at all. It was test tubes that we're using in labs. So something very different than what we're using today.
Well, that's good, because then maybe we can just take it all the way back. So why don't we take it back to like the first time that quantum computing was like really proposed as an idea, right? Let's say 1980. So who decided that we actually needed quantum computers in the first place?
Well, deciding to need, not sure that's exactly the way I would phrase it myself, but Richard Feynman in the 80s said, hey, quantum systems can simulate other quantum systems. And then it was a speech he famously gave, there's plenty of room at the bottom, and motivated physical systems that we know exist, quantum systems, to efficiently simulate other quantum systems. He knew it was a very difficult problem to do. Like it was very challenging to build that kind of hardware for obvious reasons. But that's what motivated a lot of people to at least start thinking about, well, how would we use quantum systems to actually do to do computations? And at first, that wasn't super trivial. The classical systems that we build, for example, they're not reversible. There's something called an AND gate. I have two inputs. The bits can be a 0 or a 1. And the output on an AND gate is either a 0 and 1. And I cannot reconstruct what the input was. Quantum systems, per definition, are reversible. So it wasn't actually clear that you can use quantum systems to do quantum computation, to do computations. But it was shown that you can use quantum systems to do reversible computing. In fact, you can do classical computing reversibly. So there are numerous hurdles that were overcome to show that, in principle, quantum computing, quantum systems can be used to do computations.
So what was the, well, maybe I need to understand this a little bit better, but what was it about sort of the single directionness of classical computing that made you worry that made them worry that quantum computing wouldn't happen?
So one of the main challenges in quantum systems is they're very delicate.
Mm-hmm.
Whatever quantum properties you have, they love to couple to your environment, and the quantum properties get destroyed very quickly. So that makes it very challenging to build. So at first, it wasn't even clear whether this is realistic at all, just because of noise. How are you going to construct hundreds, thousands, or millions of qubits in a way that you're tolerant to errors? And that's where, at a later time, actually, quantum error correction came in. It basically kind of saved the day for quantum computing to show that you can still do error correction. It wasn't clear at all that this is indeed something you could do, but the theory has shown that you can correct errors even in quantum systems.
So kind of breaking that down, it's like 1980 is the first time that, it's really stated if you want to simulate something quantum, you got to use a quantum thing to simulate it. But then it's like a decade and a half until, everybody's like, yeah, it would be cool if we could do that. But, we have to actually create like this huge system of controllable individual quantum things, like a quantum bit. And that is going to be incredibly hard. But it was like 1995, right? 20, 30 years ago that they actually were like, well, actually, we can do that.
Right. There are two algorithms in the mid-90s, 1994. Love Grover, he proposed an algorithm to do search on an unstructured database. And Peter Shor showed how to do factoring numbers in polynomial time. I'll get to that. In 1994. The Shor's algorithm is really what broke open the field to actually go ahead and build it experimentally. The result was really remarkable. Classically, all of our encryption is based on an unproven belief that factoring numbers is difficult. It's exponential. So if I take 15, I want to get the factors of 15, it's 3 and 5. But as I scale the number, figuring out the factors gets exponentially hard. That has never been proven, but everyone believes that to be true. Peter Shor has shown that on a quantum system, solving that problem only requires polynomial resources. So something like, n squared or n cubed or something like that, something that's not exponential. And that immediately posed, in some sense, a red flag for, hey, if you can actually build this, all the encryption that we're using nowadays is useless. There is quantum safe, so it's not like we're completely toast here if we build a quantum computer. But that certainly really sparked the interest, like, hey, can we actually build these systems?
So let me take a step back. So they thought, hey, there's this bad thing that we could do. Let's do it.
Well, I mean, it's human nature. It's like, well, I have a new hammer here. Let's see if I can actually build it.
Well,
I have a concept of a hammer. I didn't have the hammer.
Concept of a hammer. I mean, I will say that it's not like Shor's algorithm only does bad things. It's like the actual machinery of Shor's algorithm is also the machinery for like chemistry simulation and phase estimation, other things we're excited about.
Yes. So there's plenty of other algorithms that have been invented or discovered, depending on how you view it. Over the past several decades. There's actually a really neat website, the Quantum Zoo, that keeps track of all the quantum algorithms that have been discovered. It documents the speed up and so forth. There have been many, many algorithms, and quantum chemistry certainly is one of the applications that we envision for quantum computing to solve things that we need for society: better medicines, better drugs, better vaccines, things of that nature.
So maybe for these early 90s algorithms, it's almost like what really happened is we kind of figured that it would be simulation would be an interesting thing to do for a while, but then these algorithms are like, no, these things can actually do math that is beyond what a classical computer can do. So there's a bunch of potential, even if the math right now is something maybe we shouldn't be doing. There's like a lot of cool stuff that we might be able to do with access to, unstructured search speedups and factoring numbers.
It's human curiosity. There's something that could do something that no other machine can do. So naturally, there's going to be the curiosity to seek how to build it. It's never going to change.
And then the next step, though, was now we actually have to build these things. And that's when you brought up this error correction idea, which just came like a year later.
Yeah, that was in 95. So that was very instructive in giving credibility to the field that, hey, there is actually a path. Because we knew there were going to be a lot of errors. We know there's going to be a lot of errors. The error rate will inevitably be much, much higher at the physical level. So you will need error correction. So that really changed the landscape of, hey, if there's one way to do error correction, there's got to be more than one way, right? Why would there only be one way to do error correction? And today we know there's gazillions of error correcting codes. There's color codes, there's surface code, there are the LDPC codes that IBM has demonstrated in theory year ago, 24? Oh, yes, in 2024. So, at this point, there really is a very good and sound theoretical underpinnings of this field. And while there's still theoretical questions to be answered, there's still a very big hurdle experimentally to build these systems.
Got it. Well, and then, so once we started building these systems, I mean, right at the start, it was like, what the heck are we going to do, right? I mean, the very first quantum computers, as you said, were almost like test tube type things. Can you tell me what that looks like?
So when I joined the group late in 99, late 98, early 99, we're doing 2 or 3 qubit experiments. They were chemicals in a test tube. So not just single molecules. These are basically an ensemble average quantum computer, which itself sparked some interest, side debates on whether or not you should call this a quantum computer, but that's maybe a topic for a different day. Isotopically enriched chloroform was one of our 2 qubit molecules that we used. And there were other molecules. And basically, this was the very early days. There was a paper that John Smolin was a co-author on. He's, here at IBM, has been here forever. And we tried to construct quantum gates out of it. Like, how do you do a Hadamard gate? How do you do a C0 gate with those spins in a molecule? What we did then, looking back now, well, these are obvious things to do. The problems we faced back then, it's like, well, we now have trivial solutions to these things. But it wasn't so clear back then on actually how to operate these systems, so to recode the NMR spectrometer to do quantum computing.
So, all right, so there you guys are. You're like, we're going to crack global encryption with chloroform.
Well, not with a few qubits, you're not going to do much. The highlight was factoring 15 using 7 spins. So
we're going to factor 15 with chloroform. But and it literally looks like putting essentially test tubes full of chemicals into a big magnet, right? I mean, this is NMR spectroscopy. So it's basically like an MRI machine that's doing simple quantum computing. It's pretty cool.
Exactly. So these spins that we put in, they basically align or anti-align with a magnetic field, representing your logical 0 or logical 1. And these spins interact with each other. The frequencies shift slightly depending on the state of the neighboring spin. And with that, you can do conditional logic and implement the basic operations that we need to factor 15, which people will say, well, this is ridiculous. Factoring 15 is trivial.
Yeah. Well, okay. So you all looked at the test tubes and you were like, this might not work out as a computer. So at some point, somebody was like, well, we might be able to do this more computery. And who was that? Right.
So liquid state NMR itself as a technology, while there were approaches and ideas on how to extend the number of qubits, didn't look like it was the right choice technology-wise to scale. So there were many other systems at the time being proposed and kicked around as potential candidates for building a realistic quantum computer. Trapped ions, certainly a very popular approach nowadays. Neutral atoms, also quite popular these days, but also superconducting qubits. And so Yasu Nakamura at NEC in 99 had the seminal paper showing what was called a charge qubit. So he showed coherent oscillations using an object made out of superconductors and what are called Josephson junctions. Josephson junction is just this is a sandwich of a superconductor, a very thin insulator, and a superconductor. That thing acts like a nonlinear inductor. We'll leave it at that for now. And that device is a macroscopic object. Like it's a fairly big object. It's micrometers in size, yet it behaves quantum mechanically. And that was shown in 1999 as the first stepping stone of a superconducting qubit.
So this is kind of building on top of, I know that, this actually is very related to what just won the Nobel Prize this year, is kind of this macroscopic superconducting quantum effects, right? And so essentially that almost, if you take that forward, then you end up getting to the charge qubit based on that sort of, initial state.
So depending on your background, superconducting qubits was a super exciting choice. They were basically something you can construct with regular classical semiconductor manufacturing. Silicon wafers is standard. Of course, in research laboratories, you use other things like sapphire. But there's a lot of hope. Hey, if you can build this, there's an easy path to scale. If I can put 1 qubit on a wafer, well, in principle, I should be able to put thousands, tens of thousands, even more on a chip. So that was very exciting. It captured the imagination of a lot of scientists, like, hey, there might be a path. Now, of course, there was also the anti-camp. You always have that. Saying superconducting qubits, yeah, they're macroscopic. Great, you showed some sort of quantum feature lasting for a couple of nanoseconds. You will really ultimately need milliseconds probably in coherent, what they're called coherence times. Coherence times, there it is a number that describes how long a quantum object retains its quantum properties. You need that to be long. It was a nanosecond back then, and we knew you had to get to milliseconds. We know from material science and decades of semiconductor work, there's a ton of defects you need to deal with. How are you going to deal with that in superconducting qubits? So there's most definitely a camp that said, no way, this is never going to work.
Cool. So basically at the end of the 90s, early 2000s, we're kind of in this camp where the liquid NMR stuff is useful for experiments, but maybe not what is going to scale. Some people are like, oh, actually, we can just fab this like a semiconductor chip, so we have a path forward to scale. And then other people are like, yes, but we can trap these atoms and ions and actually keep them quantum for long enough to do something interesting with. So that's how we're gonna figure out the scaling. We have the quantum already versus we know the scaling, but we don't have the like high quality quantum yet. And those camps are actually we're still there.
Yep. So all these different approaches have different advantages and disadvantages, and like you articulated. Trapped ions, really very long coherence times, it became just a problem of scaling, right? Now that's been a challenge. For superconducting qubits, often it's the opposite way, that, hey, it's very difficult to get these things working well with each other. But once you do, there is a path to scaling. So there are various pros and cons. I got into the superconducting qubit work. I did my postdoc with John Martinez, who was one of the this year's Nobel Prize winners, again, for reasons that, hey, it's something that I thought could scale. Semiconducting fab exists. If we can sort out the physics, we'll be able to move on. And back in those days, certainly even within superconducting qubits, there were different styles, different approaches. It's interesting. At the end of the day, what we're building is something, you have a toolbox. The toolbox are superconductors, Josephson junctions, which are like your nonlinear inductors, and capacitors. How you assemble them with loops or wires and whatnot is up to you. But yet in those days, different arrangements were called different names. We had the charge qubit, we had the phase qubit.
Flux qubit.
Yeah, flux qubit, charge qubit, phase qubit. Yeah. They're all just different arrangements of how you put those inductors, capacitors, and junctions together. And there was a real turf war on what you should name what because of whatever property you can measure in lab. It was quite interesting.
Well, it's funny because when I was in college, I was, this was in just starting, this conversation was happening. And I remember like it being a big deal. Like, is it going to be flux qubits, charge qubits, or phase qubits? But then it wasn't until I actually started working in quantum computing that I realized like, yeah, it's just like they all have the exact same components. They're just what specific property of these electrical circuits is the thing that you're able to control and store 0 and 1 in. Mm-hmm. So in some case, right, it's like the amount of charge or, the flux through the capacitor or the Josephson junction or I don't really know what I'm talking about, but you do.
Yeah, there was a lot of research to be done. There's the trade space is quite enormous. What you really want in an ideal world is just a quantum 2-level system, a ground and an excited state, and that's it. Mm-hmm. None of these systems have that exclusively. Depending on how you arrange these elements, I can just take an L and C without the junction, and I have equally spaced energy levels. Cannot use this exactly as a qubit, although that structure is being used for bosonic codes and other things, so it's certainly not a useless object, but for a qubit itself, it wasn't considered an upfront approach.
Yeah, I think to break this down just before we go on, because I know where you're going, but I want to make sure the audience is with us, is that we need with a qubit, it's a bit, so they have two things, a 0 and a 1. And so you need quantum states that are, where you can just access 0 and 1. But the issue is that with an atom or with, any quantum system, you have 0, 1, 2, 3, 4, 5, 6, and the amount of energy it takes from 0 to 1 is the same amount as it takes from 1 to 2.
Yeah.
So you're kind of screwed if you want to compute with this thing, because you're just going to start sending electrons into 2, 5, 10.
Exactly.
So now you have these LC circuits, an inductor and a capacitor. It gives you the quantumness because it's kind of like this oscillator, so you have access to energy states, but it only gives you access to the perfectly spaced states. So you all needed to figure out, okay, well, how do we get it so that the amount of space between 0 and 1 is different than the amount of space between 1 and everything else, and 1 and 2, 3, right? Am I making sense?
Yeah,
Okay.
exactly. So you want the energy from 1 to 2 or 1 to 3, all these other transitions to be different from 0 and 1. Because then in frequency or energy, you can isolate the object and it behaves like a qubit. What we call a harmonic oscillator is not that. It's certainly a useful object. We use it for readout and other things all the time, but it's not useful as a qubit. That's where the Josephson junction comes in. It's also an inductor, but it's nonlinear. And in fact, it's really remarkable. It's nonlinear at the quantum level. So adding 1 photon of energy already gives you a nonlinearity or a change in energy to go to the next higher transition, depending on how you do it, by as little as 5% or, well over an order of magnitude.
So the whole magic of the Josephson junction is essentially giving you, if you at first you're a regular LC circuits that electronic nerds all know is essentially a simple harmonic oscillator, a pendulum that goes back and forth, and simply by replacing the inductor, the L, with a Josephson junction, you have now, it's no longer a simple harmonic oscillator, it's this sort of nonlinear system that allows you 0 and 1 and squeezing everything else
And there's
together.
many ways in which you can arrange these L's and C's. So these are the standard linear elements, and your Josephson junction, which is nonlinear. And that's where you get the phase qubit with flux qubit, for example, in the charge qubit. And they all have exactly that trade-off. So the flux qubit had an enormous amount of what we call anharmonicity. Anharmonicity is what describes the energy difference between 0, 1 and 1 and 2. So that was a very positive thing. It was a very simple object to make. It actually didn't really require any additional capacitances. So great object to study, but it had this property that is a function of magnetic flux. The way it was arranged, it was a loop with 3 junctions, and you can put a magnetic field in that loop. And that magnetic field allows you to tune that 0 to 1 transition. And if you plot that frequency as a function of the flux that is applied, you start at a very high frequency, you go down to a minimum, and then you go back to a high frequency. So there's a minimum. That's what we call a sweet spot. At that sweet spot, you're actually very insensitive to all sorts of variations. So it's sort of a conceptual and nice idea. Physicists love this all the time. Symmetry point, first derivative is 0. But as soon as you get off that spot, your T2, which is one of the Coherence Times metrics, just takes a nosedive.
Okay, so this qubit idea, you basically figured out a tuner that can get you to figure out, you get this access to these zeros and ones really nicely, except you really got to be so perfectly tuned that it might not really work.
A little bit off. And in a large system, thinking ahead, it's like, well, how do you ensure you're always going to be on that spot? What about magnetic flux noise? There's this thing called 1/f flux noise that is ubiquitous in basically all these quantum devices. It's been very well known for decades. How do you couple flux qubits together? That's the other part. It's great to have a qubit you can build, but it has to talk to another qubit in a way that you can do conditional logic. Right? And that was also a challenge within superconducting qubits. And just to make a long story short, there were all sorts of proposals on how to do this with flux qubits, with phase qubits, with charge qubits. Readout was a massive problem by then, but that's sort of a separate problem. And CQED, so circuit quantum electrodynamics, was one of the key inventions that really changed the field in superconducting qubits. And that basically got rid of the old way of reading out. The old way of reading out was very destructive. You had to use something called the superconducting quantum interference device.
Reading out is just asking what the number is, 0 or 1.
Yeah, measuring the qubits. So at some point, I have to interrogate the qubit and say, hey, are you in 0 or in 1? Right. So we use these squid devices. They're very destructive. They basically destroy everything. Wasn't even clear that is a viable path long term. But then came along CQED, where you use that harmonic LC resonator, you couple that to a nonlinear qubit, and it turns out that the linearity of that harmonic oscillator is slightly disturbed depending on whether the qubit is in 0 or in 1. And there's a very, very slight frequency difference in that harmonic oscillator now coupled to the qubit. So by asking the harmonic oscillator, what precise frequency are you actually at, will reveal what the state of the qubit is that is coupled to this harmonic oscillator. That changed the landscape completely in superconducting qubits. Everybody is now using that readout.
And that's the transmon?
You can use that readout, it's CQED, for any of these superconducting qubits. But what came along with it, it had opened the door to other types of superconducting qubits that you previously didn't consider. If you had to read out with a squid, you had to have a qubit state that is also magnetic field, that has a magnetic field that you can detect. So it was kind of a bit of a mess. That technique now says all you need is really, you don't care anymore what the actual physical property is between 0 and 1, whether this is a charge or a flux or whatnot. So that opened the door, and that's how the transmon emerged. The transmon is, strictly speaking, also still a charge qubit, but it basically tries to thread the needle on the immense trade space in superconducting qubits. So it still retains an anharmonicity, so the 0 and 1 and 0, 1 to 1, 2 energy difference is different enough that we can address it in frequency. It's not a huge amount. It's sort of 3 to 5% for most of the systems that are out there nowadays. It's relatively easy to fabricate. The capacitances you need, the critical current, which is a metric that's associated with a Josephson junction, let's not worry what it is, but all these different parameters are very reasonable to build. You can build the capacitance without having to worry about spurious inductances. You can make the junction. And both the T1 and T2 were simultaneously good over a wide range of detunings and parameter space. So that was a really, really great insight into threading the needle in this parameter space.
So taking this back just to make sure we're getting it, is that we have this sort of world of these early superconducting architectures that are emerging. The way that we actually can use them as computers essentially requires hitting them with a hammer to figure out whether they're 0 or 1 in the quantum sense, punching them, let's say, or touching them, which even that's bad. And so instead, like, the kind of magic is figuring out this kind of new technique, this circuit QED technique that allows you to essentially use another component on your chip to do the readout that you didn't have access to before. And so simply by making the readout, the deciding whether it's 0 or 1, like as simple as essentially doing computations on the chip, you fixed a lot of stuff such that you can sort of explore trade-offs and compromises between these 3 qubit technologies. Mm-hmm. And that's how we ended up with the transmon, which is essentially just like, imagine the best of all worlds from what we got with all of these existing qubit chips.
Right. And this the CQD technique basically pioneered at Yale University, which Michel Devray was also heavily involved with, also a Nobel Prize winner. So that was really, really instrumental in getting to the transmon, which is basically, I wouldn't say the only style of superconducting qubit pursued nowadays, but very, very strong favorite.
So then it was a couple years between like the transmon emerging, all the Yale people come and work at IBM, and then actually making this thing into a computer that goes on the cloud, right? So what's the sort of progression there?
Right. So when I joined here, in the mid 2000s. There was a superconducting qubit effort. It was very small. We were a handful of people, basically. Still in the days of phase, flux, and charge qubit. Transmon was sort of already a little bit on the horizon. It's not something we were doing at the time, but we moved towards that. We built a type of flux qubit that was actually more like a transmon, but we call it a flux qubit. Anyway, let's not worry about that. It's politics, basically. Soon after those early experiments, we just switched over to the transmon. And a lot of work went into, okay, so we have single qubits. We needed to get coherence times better, which we did. So some really great experiments we did where at the time we managed to get from something like 1 microsecond T1. So this is the time it takes for your quantum qubit to sit in the 1 state. It gives us a photon, it decays to 0. That's what we call T1. That was about 5 microseconds back then after the improvement. So we're super excited about that. So that was one of the research threads. We had to just get these coherence times longer. And the reason for that is because the time to do a logic operation, so qubit 1 to talk to qubit 2, to implement something the equivalent of an AND gate, we call it the controlled NOT gate, for example, takes some amount of time. And you want this T1 and T2. T2 is the phase component. We want those to be much, much longer than those gate times.
Yeah, this one actually is important to linger on, which is simply that your qubit doesn't need to stay quantum that long, but it needs to stay quantum long enough to do a lot of quantum operations on it. So, for example, if you have a circuit that you want to run like 5,000 steps on, well, then essentially your qubit needs to be guaranteed to be quantum 5,000 times longer, at least, than it takes to do a single thing to it. So,
yeah, roughly speaking. So, these gate times, depending on how you do it, and this was part of the research in those days, is how do we actually get qubits to talk to each other, also exploring a vast amount of parameter space. Do I tune these qubits in and out of resonance? Do I use what is called parametric drive, which is a microwave-based approach, basically? What is the best way to actually couple these qubits? We did a tremendous amount of research and arrived at a path that we no longer use today. Anyway, that was part of the research. But yeah, coming back to the point about coherence times, they don't need to be infinite, but they need to be long compared to doing these operations. These operations take something on the order of 100 nanoseconds, which is a very short amount of time. And you want to be quite a bit longer. And you want to be long enough so that these error correcting techniques that we talked about earlier become meaningful and relevant. These error correcting techniques allow you to exponentially suppress errors, even with just a modest improvements in physical error rates, basically. So if you're at 100 nanoseconds, a lot of error correcting codes, if you can get the error rates of your individual qubits down to 10 to the minus 4, so that's 1% of 1% in error rates. All these error correcting codes are, not all of them, especially the LDPC code looks really attractive. Surface code also looks attractive, but you still need an enormous amount of qubits. How do you get to this 10 to the minus 4 error rate? That's where you need coherence times to be 10,000 times longer than the gate operation. So you need to get to something like a millisecond, which is, I don't know how long a blink of an eye takes, but it's short. So a millisecond is not a long time. For us, for the community, millisecond is kind of really all that you need.
Got it.
For these systems ultimately.
I see. So this was something that I maybe needed help understanding, but I'm getting now, which is that error rates is different than coherence times. Coherence times is simply how long a qubit can stay quantum.
Yeah. It's a fundamental limit. If you don't have good coherence times, there's nothing you can do. You can jump up and down and run in circles. You're done.
Got it. But at the same time, to do these error correction techniques, which, kind of the whole reason that we are pursuing quantum is because we feel confident that we'll be able to do error correction. But actually getting to error correction requires that you create a system that you can basically keep it coherent long enough that you can do some number of gates on it. So basically, the coherence times has to be a lot longer than the amount of time it takes to run a gate accurately. And once that sort of ratio is big enough, then we can start to consider combining a bunch of qubits together to store extra data and build these error-corrected systems.
The coherence times, these T1 and T2 times, so at T1, again, dropping down and giving up energy. T2 is the phase component. Quantum mechanics is all about waves. They have an amplitude and they have a phase. So there is a phase coherence times as well. Both need to be long. They've set a fundamental limit to the errors of your qubits. But you can have errors from all sorts of other things that can happen. For transmons in particular, the 1-2 transition is actually fairly close in energy, and it does matter when we want to do just a NOT operation. So putting the qubit from 0 to 1 or 1 to 0, we apply a microwave tone. That is still close enough to the 1-2 transition that if you don't do anything, you just sort of boneheadedly apply the pulse, you get an error that's measurable these days. But there are techniques to fix that. But it's an error if you don't do it. If you have noise on your control electronics, you get errors. If you have unwanted interactions, so if you take two qubits and you want to interact them, but either one of those also interact with their neighbors that you didn't intend, that's an error. So there are many, many ways in which you can introduce errors in your system that have nothing to do with coherence times.
Speaking of boneheaded, which is me, so we will have something I want to do with the quantum computer. I know I keep taking us back, but I do want to make sure I get this one too. So we keep saying microwave, and I know we're not putting the chips in a microwave. You're not just like shining a flashlight at the qubits, right? Like what's actually happening in order to control and make sure they work.
Yeah, microwave, it's actually a very similar frequency that's used in your microwave oven, so hence the name. So these qubits, the energy difference going from 0 to 1, that has an energy. Energy is related to frequency by Planck's constant, and that gives us on the order of, say, 5 gigahertz in frequency.
So just the amount of energy, like the frequency of the pulses we send to the qubits is the same frequency that would heat up.
Right, so we use... like the outlet now, the outlets here, the 60 hertz, we instead of 60 hertz, we go to 5 gigahertz. So we have basically an outlet that operates at 6 or 5 gigahertz. We send that to our qubits and use that to do operations, take it from 0 to 1 or 1 to 0 in a very controllable fashion.
Okay, now let's take it all the way to the question. The big money question is like, okay, so you've built this thing and now we're going to somehow use it as a computer. Okay, but not just any computer. It's 2016. Everybody's talking about the cloud. Get this thing on the cloud. So why are you putting this on how do you put this on the cloud?
So a lot of work went into, we got to fix coherence times at least a little bit. We have to figure out a way to couple these qubits. But then importantly, some of the system engineering that is critical for things like Starling and Blue Jay, our error-corrected systems in the future, is you have to be able to calibrate them. Right? This can't be a manual process where you come in, you run something, you eyeball the data, you pick a data point by hand. It has to be all automated. A lot of work went into doing that. It has to be stable enough. This is part of the physics research that you have to do. If you have a system that you bring up, you calibrate everything, and then because of drift, magnetic disturbances, we talked about that a little bit, and just drift. It happens in these very microscopic type of systems. Depending on how you design it, if an hour later all your calibrations are off, it doesn't do you any good. These things need to be up and running all the time. That's what we figured out behind the scenes. And there was a think meeting, well, must have been before 2016, logically. I don't remember what year that was. Ike Trung actually asked a question in the auditorium, who here would use a quantum system if it were available on the cloud to either as a teaching instrument, to do science? Raise your hand. A very, very large fraction of the room raised their hand. So that was a motivator, not the only motivator to say, you know what, maybe we should do that. There seems to be interest. Let's make that bet that people would use it, because ultimately, look, these things are not going to be the size of your cell phone. These are, for superconducting qubits, you have these big refrigerators, they take up a big lab. That will not change. It's only going to get worse as you add more and more qubits. You have to have more fridges, and it just gets, so that they will not be portable at all. So how do people use them? There's cloud computing now. Why not add quantum to the mix of this? So we did that. And we had no idea really what to expect. Obviously, we were hoping for people to log on quickly and do something. And that's exactly what happened. That was just absolutely amazing. And really, it was a delight to see that we put it online. And before you know it, people are running Bell tests, so entangling 2 qubits in this special state, and doing science. And since those days, there's now been thousands of papers that have been published doing research with remote access to quantum systems. Absolutely impossible in the early 2000s, mid-2010s.
Well, this is something I tell my friends when they're, people will say like, oh, well, they're not doing something useful yet. And it's like, quantum computers have actually been doing useful things since then, because back then, before that, if you wanted to test quantum, either you had to work for a university lab or you had to just do the math and say, okay, I guess it'll work. But then from then forward, you essentially have a machine that allows you to control the rules of quantum, that you can actually study quantum mechanics and quantum physics in a way that like is real. And not only that, but you could do it like in a applet that kind of looks like, like a cute web app. Like you just go online or you can Qiskit, in a Python-based software development kit. You can just do quantum physics and watch quantum physics actually happen and be real. So that's pretty cool.
I mean, so even before the cloud, I mean, you do have some folks that say quantum computing, geez, that's going to be really hard and it's impossible to build. What's the use of it? It doesn't do anything. Just to, quote another famous example, it's like, what's the use of a baby, right? I mean, You have to nurture it and grow it, and before you know it, you might have a Nobel Prize winner. So, you know the potential this has. So it was nurtured. Did it do anything of commercial value, solving an interesting business problem in 2016 when we put it up? No. But did it do something useful? Absolutely, it did something useful. Theorists could now do experiments that they previously couldn't do. How is that not useful?
And we should go back also to the grand challenge here, which we didn't really sit with long enough, which is that this thing that essentially is imagine a bunch of needles that we're balancing on their pin, on the tip of the pin, and we need to somehow keep them all standing upright and be able to control them exactly as we desire, even though all the needles want to do is fall down. And we've figured out a way to essentially create this kind of system on a microchip and then plug it in so that everybody could use it. And the thing that with the calibration, if you're talking about these needles, it's you're not just it can't just work one time. You can't just print a chip and it's it worked. It's more you have to print a chip and then forever it has to just continue working. And no matter, even if you take the bowl of needles and you walk up the hill or you shake it around or you do whatever you need, it still needs to, this extremely sensitive system just needs to keep working. And so that's, I guess, and that's, we've talked about this in previous episodes, but it's why do you put it in a fridge, or why people, why it has to be reinforced and all this stuff. So it's actually quite an incredible feat that, this system that, again, is one of the most sensitive pieces of equipment ever that simply does not want to work. It doesn't want to work so bad. And now it's just we figured out how to make it work.
Right. We sometimes lovingly, jokingly say things. I have an idea. Let's use the world's most sensitive devices to build a reliable computer. There is a path. And certainly there's a lot of engineering. This is an amazing transition to go from the physics experiment, where you really mostly care about demonstrating a certain piece that previously hadn't been done before, or a stepping stone to get to somewhere else, write a paper and move on. We're absolutely still doing that. Not the paper component, but figuring out the science. But on top of it is now the engineering, how to get this all reliably working. And, you figure out interesting things. The earthquake we had in New Jersey, for example, temporarily killed our T2 in our devices. So
I do want to, of course, flag that it's great that we were able to build this thing, but I know that the grand challenges are still ahead of us, right? So tell me a bit about now going from 2016 to 2029.
Yeah. So what we had back then are basically quantum devices. Right? The first system on the cloud was comprised of 5 qubits. You can simulate 5 qubits, with great circuit depth. Depth meaning the number of quantum operations. Not going to do anything practical. You need to do anything practical. You need number of qubits and number of operations on those qubits. You need both. So we've since then moved towards a scale that you can no longer brute force simulate classically. That's roughly speaking order of 100 qubits and say 5,000 operations. That starts to get very difficult, if not impossible, depending exactly on what you do for classical computers. That's where we are today. That's what we call quantum utility. You can now explore scientific problems like quantum chemistry. There's something we call SQD, so sample-based quantum diagonalization, to simulate ground state of molecules, where we're getting competitive with good classical methods on 100 plus-ish type qubits with thousands of gates that we apply. So we call that utility. We're using it as a scientific tool to explore. Moving forward, error rates need to further come down. We're using techniques that are not error correction. We call them error mitigation. Those techniques themselves scale exponentially, which is not scalable, which means you can't use them indefinitely, but we can use them for now to push the reach of the qubits, the quantum systems that we have. That's what we're building with our series of Nighthawk devices over the next several years. They're going to be increasingly perform deeper and deeper operations. The big differentiator will be in 2029 with the system we call Starling. That'll be an error-corrected system. So there's a lot of scaling that needs to go in. There's a processor, which is, my daily bread and butter. It has to scale. It has to be manufacturable. you have to do, if you do it, you can't just do it once with a 1% yield. You have to do it over and over, and every time it has to work to within specs. With the error correcting codes, it has a much more engineering challenges than other codes that we use that are proposed, but at a huge advantage of 10 times fewer physical qubits, which is enormous, and we're making a lot of great progress there. Then comes everything outside the quantum processor. We have flex, we have isolators, control electronics. All of that needs to scale. So it really becomes a massive engineering scale-up manufacturing problem.
And I think that, so there's like a two-pronged approach, right? If you have this tool that does exist, that can already do things that a classical computer can't do, then there's sort of this one area that's pushing, we're going to do it twice as much as classical can do. Like, we're going to do 4 times as much, kind of with this Nighthawk chip, like, just gets you something so that people who are, kind of our early adopters can really squeeze the potential to do something useful. Because if you have something a classical computer can't do, then there's the chance to do something it can't do and make money with it.
And it's basically all analog. As the error rates gets better, we can do more and more operations on those systems, which basically will make it harder and harder for classical tools to be able to do the same thing. But one of the questions is, how do you know your output of your quantum computer is verifiable? Like, that's a hard thing to do. For something like factoring is easy, right? You can verify, hey, I claim these 2 things are the factors of some number. You can multiply them fairly easily. But on some other problems on the quantum system, that may be a little bit harder to do. So that's definitely one thing to consider. They have to be verifiable. The other very interesting thing that Shor's algorithm, Grover's algorithm, the way they were prescribed or proposed is: you come in, you go to your quantum system, you say, I want to run this quantum circuit, you hit go, you wait, you get the answer, and that's it. So it's a single execution quantum circuit. That's not at all how we're envisioning quantum systems of the future to look like. That's what we call quantum-centric supercomputing, where it's not just you go to a quantum computer, you run something. No, it's going to be a tightly orchestrated system comprising of a quantum component, AI components, classical compute components. And we already see this in some of these algorithms that we run. You run a piece on the quantum system, you get an answer, you feed this to a classical optimizer that does its thing, spits out an answer. You use that to reprogram your quantum computer, run it again, get an output, put this into your classical system, and so forth. So that tight orchestration is something that we call quantum-centric supercomputing, and that's how we believe the future of quantum computing will actually look like. It's not some single execution of something. There's going to be a substantial HPC component and tight orchestration with other compute resources.
So you do have these tools. By having this tool that can do something a classical computer can't do, then it's actually enabled us to create new algorithms that ask, well, if I have access to this kind of tool, what kind of thing can I do? And on that sort of current near term, a lot of those things are kind of essentially, we identify something that's hard classically and bring in a quantum computer to do that specific thing, but kind of acknowledging that classical computers are like the best computers that will exist for a long time for their specific tool. But then this is the second piece. So that's what we're doing that's what Nighthawk is doing. But then there's this fault tolerant thing that we also have to figure out. That kind of in the background, you have these IBM people who are sitting at the computer being like, okay, how do I connect these qubits to this? And how do I put this in a big box and get it to be the biggest box and make this thing actually not just be 4 times better than a classical computer, but like a zillion times better than a classical computer for being able to run these single shot algorithms.
Yeah, it's not quite zillions. We're expecting to go to 100 million gates as opposed to 5,000. But
okay.
Yeah, and that's where error correction comes in. This is becoming it's a very difficult engineering challenge. But we've made a lot of progress over the past year to demonstrate pieces that go into this error correcting code. So it needs a much higher connectivity between qubits, at least a 6-way connectivity. We've done this with basically the same error rates and coherence times in our previous generation of chips. You need much longer couplers in those, where you no longer couple qubits that are physically neighbors on the chip. You also have to couple qubits that are distant neighbors on the chip. That we have done at length scales that we believe are close to, if not what's needed even in the long term, with the same error rates basically that we used to show in our Heron devices. We need to have better coherence times, so we have We're getting milliseconds, like 1-2 milliseconds or so on our test devices. We're in the process of moving that technology into our error-corrected codes and into Nighthawk devices. We need to be able to reset our devices. That itself is a challenging problem. It sounds like, well, in the history of this field, you know what makes T1 bad, so we know how to do that. What's challenging is to make it bad at your fingertips without destroying anything else.
Right.
That's
The thing we want the
it.
least is for it to accidentally go from 1 to 0. But now it's like, well, how do we really quickly get to go from 1 to 0 on purpose?
Yeah. So if you have a qubit, you say you want this to be millisecond coherence times, except for when we reset it, then we want it to be as short as you can, like back to the 10 nanoseconds from the early days. But without doing anything to the neighboring qubits that you're still coupled to. So that's an engineering challenge, but we have that working with demonstrations of very short reset times while neighboring qubits being basically unperturbed. So that's all coming out. We've also demonstrated another layer routing for these error-correcting codes. It's no longer okay to put qubits like on the surface of the table with just wires drawn that never cross each other. With these LDPC, so it's called low density parity check, just for names. Let's not worry what that means.
Google it.
So their wires need to cross, right? And the way you do this is you have to have one layer that is high quality, low loss, but that qubits can couple to, and then another layer where you can, couple even more qubits in a way that would look like, if you look top down, the wires cross, but they don't actually cross. So that's also something we've demonstrated with basically the same error rates and coherence times on our devices. So we have demonstrated all the building blocks that we need for these LDPC codes. Loon will be the first architecture that incorporates all of these things into a single device, right? And that will teach us where to go from here. Right? There will be unexpected things. Some things will work better than we expected. Some things will probably work a little worse. So that's where we're going to learn from. We're going to iterate from that learning, build Kookaburra, build Cockatoo, and then a series of devices to include more and more features that we need for our fault-tolerant systems, beginning in Starling in 2029.
How does it feel kind of being, you've been at IBM for, I believe, 20 years, almost 20 years.
Almost 20, yeah.
How does it feel looking back and being like, well, 20 years ago, we were like trying to figure out the first thing about this thing. But then today, the kinds of problems you're solving are like actually bordering on engineering problems. It's not just like, okay, like if I tweak this, will the physics equations be different? It's still that, but it's like, you actually are like going to fabs and talking to people at fabs and being, like, this is a computer that you're trying to make a good computer versus this is a couple of test tubes of chloroform you're trying to make into something.
Yep. So, I joined IBM because the goal was to eventually build a system that does something for society. That's why I joined industry. That's a personal choice. There's neither good nor bad about it. There are others who choose to go to academia, which is obviously a lot more focused on papers and first of the kind type of demonstrations as opposed to a lot more the engineering. I was interested in that engineering, making it actually happen. Obviously, we were very far from that 20 years ago. We were basically, in some sense, an academic group. But always, if you look at the roadmap, even back then, from like TC, who was the head of science and technology back then, it's like, no, we're doing this to keep tearing down the walls and learning more and more physics that ultimately could become part of overall IBM's strategy. And, if the physics didn't work out, it would have been deleted. But, okay, we kept making progress and, we're still here.
Is it going the way you thought it would 20 years ago?
Well, I think you can assign probability. So it's the quantum computing is one of those notorious fields where, you talk to other parents or friends or whatever, and they just sort of roll their eyes. Geez, okay, quantum computing, good. I'm done talking to you. How's football going? It's a very, very daunting field. And back then, it was like, yeah, okay, good luck doing that. And that was basically the reaction from many other scientists. Oh, quantum computing, really? Think you're ever going to build anything with that? Jeez, okay. I wasn't super perturbed by that. It's like, okay, fine, sure. That's your opinion. We'll keep working on things. But did we think, like, what would be the probability that we'd be sitting here today where we are? We probably would have assigned a very low probability with it. But it also shows to say, you can't just get discouraged by low probability necessarily. You just You can make the future happen. Just work at one problem at a time, fix one thing after the other. Before you know it, we made a lot of progress. It went the way we hoped, obviously, but the actual technical details, geez, the number of things where you looked at and said, this is probably not going to work out, but let's give it a shot, and it worked out, is quite staggering. And also other things where you made a bet and said, I think this is going to work, didn't work out. So it's really the way the science goes can be very surprising. But as a whole, this is exactly where we hoped we'd be when we joined.
Cool. Well, I think I'll leave it at that. You have quantum computers to build, but I do want to give one final question, which is just what do you hope a world with quantum computers in it will look like?
Ultimately, where I really hope things come from is the intent is to make the world a better place. So personally, for me, I like the pharmaceutical aspect, better medicine, better drugs. For us as humans, I think is a very attractive benefit of these things. There's obviously also financial implications for companies and whatnot, but to me, the medical, the health aspect to that is important. And then there's also materials. I mean, how many materials, has changed humanity? Superconductivity itself. It's not really a new material. You just have to cool things down cold enough. But yeah, those are the areas that I really, really hope we'll find vast amount of advantage, benefits to society.
Awesome. Well, thank you so much, Matthias. This was really fun. And where else can people learn more about quantum computers if they're interested? What would your sort of advice be?
Well, first go to IBM's website.
Okay.
Naturally. We're also going to learn about quantum computing.
Well, we're in the pocket of Ike Chuang big textbooks, so maybe go buy Mike and Ike.
Yeah, if you feel up for it and you want to do some very heavy lifting on the theory of quantum computing, that is definitely a textbook to sink your teeth into.
Well, we have the best IBM is the best quantum textbook now, so sorry,
Yeah,
guys.
There's a lot of tutorials on Qiskit as well on learning it, for sure.
So thank you so much for giving me all this time, Matthias. And thank you, and I guess I'll see you around.
Yeah, thank you. Appreciate it.
Awesome. So that's it for this episode of the Coherence Times. If you enjoyed the conversation, please be sure to subscribe wherever you get your podcasts and share it with somebody who's curious about quantum. You can find us on Spotify, Apple Podcasts, and YouTube via the IBM Research Channel. And for more episodes, resources, and deep dives, please visit us at ibm.com/think/podcasts. I'm Ryan Mandelbaum. Thank you for tuning in. And remember, the quantum future isn't just coming, we're building it right now.